was gonna help. I was sick on like Thursday and I had work, but then I had blood work on Saturday. So then Saturday I just worked in the town a lot for that.
Oh yeah.
Like, all that is going on. But what I was surprised is I had white blood cells were low. I was like, I'm sick right now. I feel like they should be high.
I don't know enough about immunology.
I
No.
don't know it. Sorry, guys.
I think it depends on what stage in the illness you're in, or if you have anything else going on, like if you're anemic or something like that.
Yeah, I come home, they gave her prenatal vitamins. Yeah, the doctor said to take a prenatal with iron. But I come home and I was like.
So you're probably anemic too, so that can affect your white blood cells.
Yeah, I came home and it was like 4 days. You know?
Prenatal vitamin. I mean, they're just good all around multivitamins, especially for women, but. All right, we'll talk about. It says ethers and thiols. We'll talk about ethers a little bit, but more about epoxides. And then, so the way that the schedule is going, we're one lecture behind where I would want to be before you do the lab that's scheduled for this week. So we'll do that one next week. And today I'll just give you your lab final a week early. So you'll have 2 weeks to work on it, write it up. And then the write-up for next week's lab will be pretty minimal. So it's all right. So I'm going to give you your basically, we'll talk about the structure. Basically, I'm just going to give you a spreadsheet with a bunch of reactants, including organic materials you can use as your starting points. And your project is just plan out a synthesis. And we'll talk, like I said, I've got to finalize which synthesis each of you are getting and double check that I don't need to change anything about the assignment. So we'll talk about that in lab today. But so today's lab should be short because I'll give you your assignment and then kind of turn you loose. You can work on it wherever you want. And then next class and the class after that, we're going to talk entirely about orbitals and resonance. The last stuff we're going to go over is conjugated pi systems. And so that's actually it's a little bit different. It is one of the mechanisms will be from that chapter. And it's interesting because you have to show the p orbitals in order to get the product right. On the final. No, sorry, on the in-class final. The in-class final is going to have the same structure as the midterm. It's going to be some nomenclature, basic concept stuff, 2 pages of reactions, 3 mechanisms, and a wild card. But one of the 3 mechanisms is going to come out of this last chapter. All right. So were these the ones that you were still working on?
Yes, B and D.
Okay. So A is not too bad.
Did we get A and B? Can you just write out things?
So it's going to slice it. Ozonol is going to slice it into. After step 2, it's going to be 1, 2, 3, 4, 5. We're going to have this. And then excess with the equilibrium hydride followed by water is just going to reduce these to turn them into alcohols. So there's your final product there. Same thing here, it's just only 4 carbons long. We got ingredient reaction followed by chromic acid. Chromic acid oxidizes the alcohol, right? Grignard reagent, the first thing it's going to do is it's going to take this alcohol or this aldehyde and turn it into an alcohol. So after step 2, there's the piece we started with and we added an ethyl group. And then we oxidize the alcohol. So after step 3, it's back to being a carbonyl. And then we do the same thing. We're going to add another ethyl group.
So all step 3 did was make it a double bond instead of a single bond arrangement.
Yeah.
And 4 and 5 do what 1 and 2 do.
Exactly. So now we're going to have 3 ethyl groups attached to the alcohol carbon. You could have switched the order on this up if you had fully oxidized this. We haven't talked about oxidation starting from aldehydes yet. But you could take this and turn it into a carboxylic acid and then do excess ethyl magnesium bromide all at once if you switch the order up. But like I said, this is a standard way to write this because we haven't covered aldehydes and ketones yet in detail. Then we've got D. Followed by tosyl chloride. So we're going to turn this into an alcohol, and then we're going to turn the alcohol into a tosyl. So when we turn it into an alcohol, it's going to look like this. And then step 3 just puts that switch to the hydrogen for an OTS. That just makes that alcohol a good leaving group, right? So we could replace it with any nucleophile, basically. So it's a little bit weird to stop in the middle. Once we turn it into a good leaving group, that's usually a midpoint. But for this problem, that's where it tells us to stop. So we stop there.
And it's a lowercase s.
Yes. Alkene with an acid. So for starters, step 1 is just acid catalyzed hydration. So we're going to take the cyclopentene and turn it into cyclopentanol. So after step 1, got this. Step 2 takes the alcohol and oxidizes it, so then we get cyclopentanone. Again, we haven't learned the nomenclature for yet, but you can see where we're going with that. It ends in O-N-E, it's a ketone. So that's after step 2. Steps 3 and 4 are another Grignard reaction. Phenyl magnesium bromide followed by water. So the phenyl magnesium bromide which that one's a good one to practice naming too. It's an alcohol. So what's our longest continuous carbon chain that has the alcohol?
Just keep it one.
Well,
Okay, well, it could be 3 since it's right off.
this ring, yes. Not this ring.
Yeah.
So it's cyclopentanol with a benzene ring attached to it. So it's phenyl cyclopentanol. We just have to specify where the phenyl group is. There's one phenyl cyclopentanol. Do we have to worry about stereochemistry for that one?
Well,
We should always be worried about it,
yeah,
but
the carbon with the alcohol group coming off of it is. Oh, wait, no, it's not.
both directions are on the ringer symmetrical, right? So, good thing we checked, but no, we don't have any chiral carbons. All right, so questions on the stage. It wasn't that bad.
No, I just didn't know what to do with it.
And actually, so you'll get 2 pages of notes on the final. So we'll double the size of the cheat sheet from the midterm because I still expect you to know the stuff from the midterm.
Yeah.
And so we'll actually, the reactions page will actually be set up more like these, except it'll be like, show me the product after steps 1, 2, 3. And then it'll have steps 4 and 5 over here. So I'm gonna test you on 2 reactions at once, basically.
I mean, I draw out the set.
Right.
This year.
It's just a way for me to give you, to test more than one reaction or one line on the test, so. All right, how'd the Williamson ether synthesis go?
I felt okay about it. Yeah,
So for B, neither of them is phenyl.
No.
And neither of them is tertiary, neither of the carbon is attached to tertiary. So you can go either route. We have 2 options here.
I thought it said show all, so I'm like, well, I thought it told me to show both.
Yeah, and that's fine because that's usually what we want to do anywhere. One out and take one that makes the most sense. In this case, we could either have,
So I did not decide on one. I totally do it. Strong should be when I said basic. Oopsies.
we could either have this as our halide and isopropanol as our reactant. So we need to deprotonate it first. So either sodium metal or NaH. To deprotonate it, that takes the hydrogen off there. Or we can switch these and have this start as the alcohol. NaH, and then plus which of those makes the most sense? Or are they equally valid?
I think they're but I was probably. I also read this wrong. I just drew the arrows. I said 1 NaH arrow 2 RX. So,
Okay. So we just want to be more specific with the R's. Either of these would work. I think this one makes the most sense. It'll be faster because you're doing an SN2 reaction on a primary carbon instead of a second carbon. So make your nucleophile a little bit smaller, and then have your lead group on the primary carbon would be a faster reaction. and the other way, they both work well in this case. Here we've got a methyl on one side and a tertiary carbon on the other, so this one we're not gonna have options. We can draw them both out, but only one of them is really valid.
Yeah, I drew on both sides again, I thought.
Yeah.
We can't read today, Thomas.
It happens. I think everybody's really tired right now. It's that time of the year. We lost an hour.
Everyone's sick.
I had 35 students in my M100 class yesterday and not a peep out of anybody. It was dead silent for 2 hours.
But isn't there supposed to be like 20 more people in that class?
Yes. But they figured out that I record the lectures, so a lot of them have stuff. I usually see the ones in person are the ones, either the best students or the ones who have lab time. Because if you've got to come for lab anyway, you might as well come for lab. So this is an option, because then we can do methyl iodide as our second one. If you wrote methyl bromide, that would be full credit as well.
Yeah, I thought we had to use the bromide at the time.
Bromide is your safe bet. With the really small ones, we use iodide a lot of the time just because it makes it heavier so that it's actually a liquid at room temperature.
Breakfast considered Williams or it adds even.
No, Williams is just you deprotonate an alcohol and then use it as a nucleophile to make it heat. So it's not as specific as you were thinking. If we tried to go the other way, if we had methanol, NaH, and then this one would use a bromide because we don't need to worry about keeping it small enough. This is definitely going to be liquid. If you put methyl bromide, I would mark it down.
I did many of my arrows. I drew everything out.
That's fine too, like we did over there.
Yeah.
Yeah. This is not going to work as well because the target for our nucleophile is a tertiary carbon, so it won't go through an SN2. You actually be more likely to get a elimination product if you try to do it this way.
Like we get in SN2,
It won't, this one won't go through an SN2 in the second step. So you're more likely to see an elimination. So what we would actually expect to see here is not an ether. We would probably actually get this as our product. Because tertiary carbons, even if it is a good leaving group, tertiary carbon won't go through SN2.
Sometimes when I had this next one really well, and sometimes it comes in the circle, it's like not even close but, and sometimes it just like makes a weird ass shape, and it's like, this is what you were trying to do, right?
I feel like a lot of the, because that's basically like predictive text, right? I feel like a lot of times when they push a new update, it wipes the things you've already taught it. So like once every other month, I have to remind my phone that dash is actually a name and should be capitalized. So is valence. So how was your day off from physics yesterday? I heard Bruce was. He's got baseball fever or something. He's now sick, right?
So
Oh,
what? I was the first one done. I finished in 45 minutes and I actually felt really good.
Good.
So it was kind of like a day off because I just came in,
Correct.
Write that test out and let, so.
Nice. That's a good feeling too.
Here with it.
Yeah, he's under the weather on his way back from Houston right now, I think.
So first week, our manager is on maternity leave.
So you've left to your own devices.
No, so our supervisors are super stressed, like, I was gonna be super stressed, but I'm crazy, but I don't have much impact. So that he like yelled at me in winter the other day. For both like, what the fuck? He's like, I'm so sorry. I'm so sorry. It's not that big. I did not like seeing
See?
like any of that. As soon as it's no, it's like seeing into the mist. He was not.
You gotta pick one.
You haven't taught us how to name something with the chain that's a methyl ethyl, so I from methyl ethyl. Well, it sounds like he did in parentheses, but the number's not in the parentheses.
All correct.
I just process a little bit.
Yeah.
Space.
Exactly. That's why we spend so much. Why I emphasize using the parentheses, because when you know how to use the parentheses, you get something totally new. You can figure it out.
Like how I was telling her for the ethers that the ethoxy, you don't name with your longest continuous carbon chain. Right, like your parent molecule is bigger and then have your ether, and she, I put that between that.
That's fine.
And she did not like that. She's like, no, actually have to continue to carbon chain. I'm like, no, right, that's for the epoxies. And she's like, shut up, go away. I don't. You have to.
Longest continuous carbon chain that has the oxygen
Not for the ethers.
for both.
See? Do number one.
So without worrying about the stereochemistry here, it's going to be a cyclohexane, methyl cyclohexane is our parent molecule. And probably put this as 2. And on 1, we're going to have 1 ethoxy.
That's what I was trying to tell you. That's what I put, but I also put 4.
So and actually, we actually want to specify both of them. There are 2 stereos. So we have to say it'll be. So there's our highest priority, then here. But the hydrogen is sticking out towards us. So it's R, but it's backwards. So it's going to be 1s. And then for carbon 2, our priority goes 1, 2, 3. Hydrogen's already into the board. So it's also S. So 1s, 2s. 1 ethoxy, 2 methyl cyclohexane. You can't just say trans because there's a trans isomer that's 1R, 2R as well. So if you specify both of their stereochemistries, though, you don't need to say trans because they have to be trans to get the stereochemistry. So D is really the trickiest one.
Yeah. Well, if B is just 1 ethoxy, 1 methyl.
No,
What would it be?
it's not a methyl group because all 4 of those are part of your longest continuous carbon chain. So it's butane. So it's ethoxy butane. You just have to specify your stereochemistry. 2 ethoxy.
No, maybe. No, easy. I know. I was like, okay, but
So priority for this carbon is going to be 1, 2, 3. 4 is already into the board, so it's R. R 2 ethoxy butane. The R part. Yeah. At least we're still good at doing our stereochemistry. That should be like second nature by now, right?
Once I hate it, it's.
You don't have to like it, and you're better at it than you say you are, because you wouldn't be getting the grades you are on tests
Yeah.
if you were actually as bad as you say.
So bad at this, guys. I'm just gonna get like a 95. It's horrible. Okay, it's all have to do really bad because like she would set the freaking current by oh, Ellen was really good. And then so like in bio too, she was like, Taylor, you're the one setting. Yeah. Yeah. So there's a problem.
Well, somebody has to set the curve.
But it was like drastic. I'm like, we don't got this. We're gonna fail. We're gonna crash and burn. And everyone walked up to me and I'm over here with like a 95. But like, how did you have my presence? I'm doing
You're good at taking tests. You don't think you are.
But like, I get so nervous.
That's
I'm
fine.
not good at it, you know.
Healthy level of anxiety is okay.
They don't get double tested. And I'm pretty sure that's illegal because my 504 states that I have to have double time. And they're like, we have our own thing. We're gonna clear you for 1.5. And I did it and did that. Okay, we'll clear you for 1.7.
It's a process.
It's illegal, I think, but
I don't
it's
think
gonna-
that's, I think it's because it's Nevada. I don't think it's federally protected. Like there's some amount, federal government says the colleges have to have some amount of accommodations, but the actual procedures, processes is up to the states.
Is maybe 13.
That's the other thing about IUPs, is they're supposed to be temporary.
Like,
Because-
not,
Okay,
it's not.
so but that's probably what they're used to.
Yeah, here, you know, like, they were like, right before, and I was like, yeah, before, and when we're not, yeah, oh, okay. But they're like, this is really old, and I'm like, yeah, because it was really expensive to get, and I'm doing it again, like.
All right, let's do this last one.
But this one doesn't have stereo, right? The two left oxy for me. Correct, we did that one,
This
correct?
one, yes, no stereo center. This one is gonna have a stereo center, and we're gonna do it just like we did here, where we're gonna say both of them.
See, I don't stairs.
I mean, you could make the argument that you could just say that it's, if you treat this, the epoxide like it's an alkene, you could say E versus Z. Because it's really, if you look at this carbon chain, 1, 2, 3, 4, 5, it looks like it's E, but the problem with that is that there's another stereo center. Or another stereo isomer that's also,
Why is it's like singular, like, no, it was down to that.
5.
I guess like 4 because I'm wondering on the triangle with the O doesn't count as a ring. No,
It is not.
okay.
Epoxides are their own thing.
But you don't have.
Good question.
So,
You have to, because otherwise we never have an epoxy on with anything other than ethane. But that's a good semantics question that I hadn't thought of. You're absolutely right to second guess that. So 1, 2, 3, 4, 5. So it's going to be pentane. I can't help that. I'm not a math teacher.
I was like, yeah, that's what it's butane.
And
You
so
can
it's
see my numbers. I go 1, 2, 3, 4. I stop at 4 on the. Boom, done. No, it's not done.
so 1 phenyl, 2, 3 epoxy, pentane. Then we just have to do the stereochemistry. So priority is going to be 1, 2, 3.
Okay.
Because you can get to the oxygen 2 different ways. The oxygen is your highest atomic number, right? So one step the oxygen, two steps the oxygen, and then this benzene ring is our third one. So 1 to 2 to 3, so that's going to be 2R. And 1, 2, 3. So that looks like S, but the hydrogen is pointing towards us. So it's R, so 3R. 2R, 3R, 1 phenyl, 2, 3 epoxy pentane.
So sorry, I forgot.
But you won't do that on the test now, will you?
Well, will you shorten like that on the test? Like this was the first time you've seen him like that.
I reserve the right to shorten them that way. It's a pretty common way to do things. You just have to remember ET is ethyl. And so if it's helpful to you,
It's an apple.
so if it's helpful to you, draw it out as cards instead of writing ET. And because if you had it drawn out, one, two, three, four, five.
Right.
Yeah.
No, it's
Going so fast. All right, this is Barry Sharpless. He's won 2 Nobel Prizes in chemistry. One in 2001 for the reaction we're gonna study next, and then in I want to say it was 2018 he won another Nobel Prize in chemistry, which was a really quick turnaround, frankly. It's almost unheard of for someone to win a Nobel Prize based while they're still working, even for the most part. Usually it takes 20 to 30 years after you do your research before you actually get recognized for it. So for him to get 2 of them so close together was a really big deal. And what he figured out is that if I go back to this example, this was 2R, 3R. But if we use our regular oxide formation, we started from an alkene. And we had equal probability of coming from the top or the bottom. So 2R, 3R versus 2S, 3S should be equally likely if we use that Rocco reaction. Sharpless figured out that if you use a catalyst that is itself chiral, you should be able to favor one transition state over the other. So basically, if we look at formation of an epoxide, the blue line is just uncatalyzed. The red and the green are catalyzed, are the enantiomers that we can form, and you can see that the red one is much lower in energy. So by using a chiral catalyst, we're able to preferentially form one of the products, one of the enantiomers. Right, so this one is a very specific reaction. It gets taught, basically, this is the one that he first proved that this was possible, and it sparked a whole new subfield of organic synthetic chemistry. Because as soon as you realize you could use a chiral catalyst, they started testing chiral catalysts in every catalyzed reaction they can think of. But they were unaware of it, so I feel bad for you because they didn't have to work.
Now we
So for these are the reactions. I'm not going to test you on the actual structures here. The most important thing is that we recognize these 2 things together with a peroxide are going to make epoxides that are stereospecific. All right, and the way to keep track of this, is they don't label them as R versus S. Go ahead.
Arrow? Or
That, yeah, this whole thing, sorry. This whole thing together gives you stereospecific epoxidation. All right, and the way to recognize this, which one is going to make which enantiomer, it all has to do with this oxygen here. This alcohol on your reactants is going to help you orient things so that you put everything in the right spot.
You said it's stereospecific oxidation.
Epoxidation. We're making the epoxide. All right, we're not going to get into the mechanism here. The way we're going to remember this though is when you get one of these, so nice that the actual title is in the black, right? It's the sharpless asymmetric epoxidation. So they got asymmetric, not stereospecific, but it means the same thing. So you take your alkene, and it has to be an alkene that has an oxygen that has an alcohol in the allylic position. So, like I said, very specific reaction. This reaction only works with that whole set of alkene, one carbon, OH. And so you take your alkene and you lay it flat coming into the board and out of the board, and you put your oxygen in the back right. Your alcohol goes to the back right corner. And if you do that, then the plus stereoisomer plus BET is going to put your oxygen above. So that's easy to remember. Plus means up. And minus BET is going to form the epoxide below your carbons. And just because we don't use this style of naming asymmetric or chiral materials very often, this plus versus the minus is instead of R versus S, because this BET actually has two stereoisomers. The plus versus the minus has to do with which direction it rotates polarized light. Polarized light is light where the light waves only go up and down, right? Or it's going to go and you basically remove half of your photons and only let the ones that have the waves facing the right direction. It turns out chiral materials rotate polarized light. So they're also called optically active for that reason. Optically active materials, if you pass polarized light through them, it's going to rotate that light either clockwise or counterclockwise, depending on the stereochemistry. If it rotates it clockwise, we call that plus. If it rotates it counterclockwise, we call that minus. So that's actually more commonly used in biochem. And in fact, you heard of dextrose before? Dextrose is just glucose, but it's glucose that preferentially rotates light clockwise. That's for right-handed. when glucose is in its chain or in its ring formation, it'll stay locked into dextrose. So as soon as you let it open that chain up and become the long chain formation instead of the ring formation, then you lose that stereospecificity and it's not dextrose anymore, it's just glucose now. But if you see dextrose, it's just still just glucose, it's just a specific stereoids from it. So you can also call dextrose plus glucose. Because the plus means it rotates like clockwise. All right, so what does this mean for us? It means that the plus and the minus, as long as we orient it properly, the plus and the minus are going to tell us where to put the epoxide. So you set it up so that your alkene, I'm going to say this again, this is the tricky part. Your alkene is into the board, down the board, with the oxygen back into the right. So you just take your molecule, you spin it so that it has that orientation, and then plus puts the oxygen up, minus puts the oxygen below. So let's try it.
You do the first one together.
We sure can. So this one's laying flat here. The oxygen is already on the right hand side. So I'm just going to take this and I'm going to flip it out towards us. So the oxygen is back into the right. And it's a plus BET. So that means when it's facing like that, our oxygen is going to go up above the ring. So then if I draw it flat again, not even convex, that's concave polygon. What are you doing, Apple? Yep. It makes sense to do that, right? You can do that without throwing off any stereochemistry because it's already plain.
Yeah.
So you can just flip it. You flip it out towards us. It's a minus, right? So that means it's going to go below.
I have my orange spread on. Instead of,
Over this way? That's fine too.
well, then we need to copy it. that's not the stuff.
Careful with that though, because it'll usually do a mirror image when you do that. So if you have a stereo cast, you have to be careful that you didn't switch one of the stereo isomers.
Like, it's still pretty.
So, but that's still, it's still not actually rotating it, it's still taking a mirror image of it, which works in this case. But if you actually had this molecule and you try to flip it that way, you're gonna get the opposite stereo isomer. So you should have to be careful. But for this one, because the active group is planar already, it doesn't matter. So see, you can take it and rotate it. But then it's still gonna look more or less the same, right? When we rotate it, we get this, then we're gonna get plus, so the epoxide is up. Means this one's gonna be down.
That is not.
So you gotta spin it so that. So in this case, as long as it's planar. You might be able to start visualizing these things. To do on your in your head, but you're gonna want to spin it so that the OH is back into the right. So if I was rewriting this. I would write it like this when I spin it, right? I just rotated it 90 degrees.
Okay.
And then we can say, okay, it's a plus, so it comes out towards us.
You would spin it like that. Instead of like.
Yeah. And on your tablet, the rotate command won't flip anything. It's only when you say flip that you have to watch out for your stereochemistry. But if you just say spin it 90 degrees, your letters might be facing the wrong way now, but everything should stay in the right position. All right, and this last one, they're all methyls attached, right? So we're going to do the same rotation we just did. So now it's going to look like this. And it's minus. And you actually get a wedge drawn really nicely. It's actually very satisfying color in the whiteboard marker. You two seen those Japanese little sticker scenes
Yeah.
that you can get? Laura's really into those right now. She finds it very satisfying and soothing if they with tweezers with the stickers just the right spot.
I like watching people do them that I already like am that paranoid about my Legos. So they already like I normally use like the order scheme to get to take off the Legos. You use the end of it. they say.
And that explains why. What's your favorite Lego set that you have?
I don't remember what they call it.
Ooh, that one of the ones.
They're all Star Wars sets, and it used to be the biggest Millennium Falcon until they come out with like 2000.
Yes.
Or my Star Destroyer. Actually, I have an AT-AT one there.
That's it. So Laura built that one. Laura was a nanny for 10 years. And when we were in college, she built that with a 5-year-old kid. It was the kid's AT-AT one, but it was the full size one.
Yeah.
And so they spent a whole summer building it with the 5-year-old.
Right? When I didn't have a dog. My parents made us a dog for Thanksgiving dinner for Christmas. And then I'd sit at the table and just finish it in like a week.
There's this woman on YouTube that does Lego builds, and like she like got the Lego Trevi fountain from Rome, and then she flew to Rome and built it overnight at Trevi fountain. She does weird stuff like that. She built the Pirates of the Caribbean set while she was on a cruise.
Oh, that's see, I only have Star Wars.
Only Star Wars stuff. I suggested, my parents were looking for a Christmas idea for me, and I suggested the $300 Dungeons and Dragons set. Like that's not appropriate for a 40-year-old.
I agree. One, the Death Star.
The Death Star is pretty cool.
Not the weird one. Like that's like not the computer. It's like this big, but it's
Right.
That's like a half circle.
Yes, those ones are super cool. All right, let's take our break. Oh, that's right, no break today. That's why you were here early. I was late. I was very kind of you to not mention it. You're still doing it. Yeah. All right, let's power through. You need to be done at 11:30. We got time for that today. So this is review. So we've already talked about epoxides and ring opening, right? Once you get the epoxide formed, the number one thing that's going to happen with it is you're going to expose it to a nucleophile, and you just do it in SN2. So what does that look like if your nucleophile is cyanide? And you're starting from this molecule here.
Is it one end is gonna become OH and the other cyanide is gonna be this?
Exactly. So we have to decide which side cyanide gets attached to. So think back to our Markovnikov reactions, Markovnikov hydration, where we had that mercury in a 3-sided ring. So if it looked like this, where all the R's are carbons, we had to choose between our nucleophile comes in and attaches the more substituted carbon or the less substituted carbon.
Now we're just choosing that for this.
We're going to do the same logic. So back here, it was Markovnikov hydration, right? So we put the oxygen on the more substituted carbon because this bond is weaker. Because it being more substituted means this is more stable as a carbocation, which means it's easier to break this bond than this side. So same logic here. Our nucleophile is going to come in and attach the more substituted carbon from the opposite side. So you have to watch your stereochemistry here. So then now our intermediate is going to look like this. This side didn't change at all. this side, the ethyl that's going back into the board is still going into the board, it's just up now instead of down. And then we have this longer 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. And then the water step is just proteins here. All right, so the trick is, remember, it's coming from the opposite side. And your new nucleophile is going to go to the more substituted carbon. Because that's the weaker bond, the easier bond to break.
So our final one looks like.
So the final product. It's just an OH. Easy peasy. We've now seen enough mechanisms that you've seen most of the possible steps, and we've already dissected a lot of the fine details. We just have to remind ourselves sometimes.
And we choose them and they're substituting. This one.
Correct.
They always come up with this. And we just show them a horrible example. Let's look at this.
This, I chose an example that where the stereochemistry, where we end up with 2 stereo centers so that we have to be careful. That is probably what I will do on the test as well. If I give you a question like this, I'm not just testing, do you remember that it's ring opening reaction, I'm also testing, do you remember, does it go more substituted or less substituted, and can you get the stereochemistry? And 3 out of 4 points would just be getting here with the stereochemistry messed up.
We can have our chemical boxes, right?
Yeah.
Some more people are interested in these, like a mole use, basically, and then I can like turn it on the computer and do like that. Okay.
I mean, honestly, the way that computers are kind of part of everything now, it wasn't when most people teaching organic chemistry learned organic chemistry. I didn't have the option to have a 3-dimensional computer screen piece. We had the models, obviously, but there was a much larger emphasis on, no, you need to learn what this looks like, be able to picture this 3D in your head, because you wouldn't be able to just throw it up on Moldio. So there's a transition for sure.
That, like, everywhere. It was like.
I'm trying to think if we were allowed to use, I don't know if anybody asked to use their model kit on any of the midterms. I don't remember if anybody did. Yeah.
Yes, no, I do this. And like my particular response was like, okay, I'll bring a small house. Ever. They're like, eat on the street. Yeah. And then what happened?
You were vindicated. They still teach them that they have to. So it's interesting watching my kids go through elementary school. They still teach them they have to be fluent in their math facts, the way they say it. Basically, you have to be able to do basic arithmetic in your head, because nobody should have to pull out a phone to do 31 plus 70.
Right, sure. But on an exam, I still check them.
Yes.
Like, is it still this number that I know my level?
But yeah, so you probably remember in 4th grade when you had to memorize the your times tables, right? And then you had like a timed test where you had to go really fast or else you weren't going to finish. They still do that.
Something like that.
Oh,
like allergic to peanuts, so ours was really scarce. Which was not as fun as theirs. Well, he doesn't have that Milky Ways. I still love you. Everyone gets Skittles.
Milky Ways are the best. All right, so for each of these,
Yes. Oh, this one. They look the same.
it's the same starting material, all that's changing is your nucleophile in each case.
Do they know how to do these new nuclear files? Yes. This isn't what we just did. This is new stuff.
It is what we just learned,
What?
but it's also, we've also seen it before.
This isn't for everybody in black and blue labels.
No, not like that.
So it's not what we just learned. Correct.
Yeah.
It was like one where you like do it like 3 different and then we had like a tree that like we would post them like the month. It was the same.
Yes. I see what you're saying.
When we see the C next to the N, for the last one you had us do like C triple bond N, is it always like that?
That's the structure of cyanide. So cyanide, the lipid is polyatomic ion. So you may not have looked at the Lewis dot structure for it. The Lewis dot structure looks like this. And so that gives a negative charge to the carbon. So the carbon is going to be where you attach it. Or what the carbon is the nucleophilic.
It's just first time seeing carbon juice like that in this class.
We touched on it back at the end of last quarter, but we didn't do a whole lot with it. So it's understandable that you forgot. Same for C. C was on our list of possible nucleophiles.
Sneak,
SNE, Nesne,
what was this?
usually it was probably written as RS with a negative sign. Our list of strong versus weak nucleophiles, strong bases versus weak bases. It was definitely on there, but we haven't talked about sulfur much. That's the second. Then for D, they had hydrogen. So we actually lose all of our stereochemistry in D because then we're going to wind up with two identical hydrogens attached to this carbon. Two identical hydrogens attached to the alcohol carbon as well. Right, so it doesn't matter what your nucleophile is. Anything with a negative charge, when you put it with an epoxide, it's going to do the same thing.
I'm understanding where like the thing we're adding on the bottom right is. I'm not understanding where. Why is it NE in the bottom right one and not CH3 and H4? It's the same thing.
It's the same thing. CH3 is a methyl group, right? So I just.
It's like really. It's not. Right?
It's not.
So I see right here, but it's
Yeah. And it does save you one letter. That's why it's way more common to see it for ethyl groups or for phenyl groups, because then it saves you a lot. Be it for phenyl or UT for ethyl.
So is that?
No, it's the methyl group.
No, it's not.
Yes. Yeah, so if I was showing that the entire structure of what we just made, because I then had to, I don't know, name it or something. Look like that. So if we do this, most of our nucleophiles are bases, right? So for the most part, we do these ring opening reactions under basic conditions. We can do them under acidic conditions, especially if our nucleophile is going to be the conjugate base of a strong acid like HBr or HCl. If it's under acidic conditions, then we just propionate first instead of second. But it's the same net result. Protonate the oxygen makes an even weaker bond, and then we do the SN2 attack. I'm going to skip this one. This is practice drawing the mechanism in an acid catalyzed situation. So you're going to start by protonating the alcohol, and then our ethanol can come in and act as a nucleophile. It's the same net result. So I'm going to skip this for now so that we can talk about thiols. So new functional group that is substantially similar to alcohols, hence the name. So anytime you see THI or especially THIO in chemistry, thio means sulfur. Generally speaking, it means you took an oxygen and you replaced it with a sulfur. So for instance, if you had, this is the structure for cyanate, which is another polyatomic ion. So OCN or OCN with a negative charge. Thiocyanate, you just replace that oxygen with a sulfur.
Is the OL is right?
OL is alcohol. So a thiol is an alcohol with the sulfur instead of an oxygen.
I cannot spell. I tried to spell beans wrong. And I don't know the
I'm gonna have to follow you around on this tour just to see how it all goes.
It's just really intense. I'm just like the extra person to be like, no, we're not stretch, you guys.
So there's one other prefix that gets used instead of thio sometimes being a sulfur. This comes actually from I believe it's Latin.
It's just both. I don't know.
If you need to name, if you have another functional group present, you can name the thiol with a prefix. Turns out most of our functional groups have a prefix version and a suffix version. Based on priority, basically, what's most important gets the suffix, and then everything else is named with a prefix. So for an alcohol.
So you said this is if we have to name two functional groups. Right?
If we need to do two functional groups at once, or if we're starting from something that has a common name. So for instance, like acetone looks like this, right? If I put an OH on it, and it's still name that as an acetone, I would just name it hydroxyacetone. If I was naming it with the alcohol as the primary functional group, I put OL at the end. But if I already have a name for the molecule and I just want to amend it, you can just throw a prefix. All of our functional groups have a prefix, like 4O.
How would you, would it be a promo or would it, or how would you name it the other way?
So we haven't gone over ketones yet, but this acetone's IUPAC name would actually be propanone. So, and then I would just say, okay, well, if there's an OH group, OH's prefix is hydroxy. So I'd say hydroxypropanone.
What if we're using?
There's basically a list of priorities that we go in order that determine who gets to be the suffix, what functional group gets to be the suffix.
You use something.
So if it looked like that, yeah, the double bond is what made it take priority. If we did it like this, we'd actually name it as a diol.
Name a double bond as a chain.
Right. Especially if it double bonds to an oxygen, because the oxygen is not part of a continuous, the longest continuous carbon chain. But basically, this is worth talking about right now since we're. No, this is one that I don't always bring up because it really is a little bit niche in terms of it only matters when you have multiple functional groups on the same molecule, or you have something that has a common name that then you amend it. But if we look at our textbook, not Gen Chem, I want OChem. What am I doing?
Like abstracts and sorts. Yes.
I think we're doing that next quarter.
And you need to work together and then present it that big group.
Yeah. Yeah. So if you go down to our textbook, go to the first appendix, it's nomenclature of polyfunctional compounds. Basically, this tells you where you can find all your different nomenclature rules. And if I scroll down though, there's a table. Basically, the closer it is towards the top, the higher priority it is.
Okay, where on this? On this one?
No, not even close.
Next.
Right. But so this is more just because we're talking about the fact that thiols have a suffix version and a prefix version. Everything it turns out does. Name is a suffix for carboxylic acid. You drop the end and you put oic acid. Thiols not on this. This isn't totally comprehensive.
Yeah. Given to us in our notes.
Maybe I'll consider that.
Priority of it. But like on.
Yeah. Something similar, but the main point I was just putting on here is that so there's alcohols OL, or if you're reading it as a prefix, it's hydroxy. It is pretty low because all of these ones have pi bonds. So if it's got an oxygen or a nitrogen and pi bonds, it's higher priority. Yes. So we would just indicate it with where it is. So if it's so if we had this molecule, this is a carboxylic acid, so this would be propanoic acid. and then we would say it's 3-oxo propanoic acid.
And that's because our outlet lines and our ketones.
Exactly. So the ketone version would just be here, and then it would be 2-oxo propanoic acid. Right. Exactly. So oxo is just the prefix meaning a simple carbonate. And then the numbering tells you if it's a ketone or an alcohol. All right. And there's more details and more practice here. If you wanted more practice, would be a good thing to go over just before you're going to take, MCAT or something like that, where you think if there might be a section on organic nomenclature. I don't know if that's on the MCAT or DAT. But if it was, I probably wouldn't go back and reread all of these sections because we've put in the work to learn it pretty well now. I would go back here, review it, double check that I understood how the parentheses work and everything, and then double check this. Make sure I remembered it all. All right. So it's a thiol if it's the only functional group present. If it's not the only functional group present, we're going to name it as a prefix, as a substituent, which looks totally different. It's called mercapta, which sounds like a Marvel supervillain because they came from different places. I believe thiol comes from the Greek and mercapto comes from Latin, but I might have those backwards. Mercapto, they call it mercapto because they didn't understand why, but in ancient Roman times, they knew that if you exposed mercury to sulfur, it captured mercury. Basically, it made a really, really strong insoluble ionic compound called mercury sulfide, which has a mineral name called cinnabar, which also is a color. It's like a really deep brick red. So this would have been in I want to say the first 1,000 years.
See this.
They didn't. So they knew that that's what mercury did, or they knew that that's what sulfur did to mercury. So they called all sulfur mercaptans. Mercaptans were just anything that you could put with mercury and capture the mercury. So they didn't know why it was happening. They just knew that the mercury went away. And then so now fast forward to organic chemistry, and they're coming up with these different names. Rather than say 3-thio, they said 3-mercapto for whatever reason. Because it was still commonly used. So for instance, dimercaprol, two mercaptans and an OH. This is the common name. This is the IUPAC name. 2,3-dimercapto-1-propanol. I don't know. Mercaptan is kind of a cool word to say, but I kind of would prefer to just say thio because it would have made life easier. But they didn't. So we get both versions. And it still gets used the same way as it did in Roman times. They didn't understand that mercury is toxic to you, so they didn't understand why or that they should be removing it from things. But now they use this as a way it will react with mercury in your bloodstream and put it into a form that your kidneys can flush out. They used to, they actually used to eat mercury because they thought it purified you, like doing a detox. And they gradually got more and more insane because it's neurotoxic and accumulates in the brain, which I'm sure you've heard of the Mad Hatter from Alice in Wonderland. Because they used to actually use liquid mercury to flatten the brims of the haberdashers, the hatters, would actually slowly go crazy over their career. Because they would wet the brim with their fingers and then they would put mercury on it and then they'd stick their fingers back in their mouth. And so they would gradually accumulate mercury. So the Mad Hatter is actually a historical thing, not just from Alice in Wonderland.
All right.
Yeah. All right. If we're trying to make thiols, it's just another nucleophile. So as long as we have a halide or a good leaving group, we can just use it as a nucleophile to do an SM2. That's our easiest way to do it. So there's some practice problems here that I'm going to skip over.
Fine.
Yes, because otherwise you're gonna hide. If you did NASME, remember that one we had a second ago? Has a methyl group attached. The sulfur will still act as a nucleophile, but you're not gonna make a thiol. You're gonna make something that looks a lot like an ether instead. That we call a thioether. I don't actually know how. I would have to review what the nomenclature is for thioethers. It's a thiomethyl group or something like that. But that's the set. If we want it to be an SH, we have to use SH as our nucleophile. So if we're trying to make a thiol, we want to use SH. So for each of these, you're just going to start with a bromide attached where the sulfur is. Let it react with sodium thiol. But this is the part that is, we'll do this. We're almost done. I'm going fast here. Finish these slides. This is the part that actually is really relevant to biochemistry because there are two amino acids that have sulfur in the side chain. One of which is a thioether, leads methionine. Yeah, methionine is a thioether. I believe that its structure looks like looks like this. This is our amino acid methionine. But the other one is a thiol. So methionine gets used because sulfur doesn't show up very much in other places, and this isn't a super useful functional group, super useful amino acid to build on its own. It gets used as the trigger to say that, okay, we're starting to make a polypeptide. Thionine is the first start codon. Cysteine doesn't get used that way because cysteine will do this. Cysteine is, I think it's 2 carbons. I think the R group is CH2, CH2, SH, but maybe it's only 1 carbon long. So it would look like this. So amino acids all have this general structure. The only thing that changes is the side chain. So the side chain, so a lot of times you'll just see them written as, there's your generic form for a amino acid. If the R is CH2, CH2, SH, it's cysteine. And cysteine is really, really critical in a lot of places because if you wind up with 2 cysteine side chains next to each other when your protein folds up, it'll actually make this disulfide bond. They'll react with each other, and it happens pretty easily, and it is reversible, but it doesn't reverse easily. You are making a covalent bond between 2 things. So basically, this thing gets used as like almost like a safety pin You have your big protein all sort of folded around and you want to make sure it doesn't mutate or unfold. If it has two cysteines in the right spot, they kind of block it together, like pinning fabric together. It can be undone, but not easily in a biological system.
And that's the one we're using now, is this.
So cysteine has this shape to it, has this style to it. So thiols are going to make this disulfide bond.
So just the R.
So just the R group. So ignore the amino acids for a second. All I'm showing you on this slide, really, I'm just giving you a biology context for it, is that if you put two sulfides next to each other under basic conditions with bromine, they'll turn into a disulfide bond, and you wind up linking your two things together with this sulfur-sulfur single bond. Obviously, we don't have bromine in biological systems, and we're not under super acidic or super basic conditions. So it's a different mechanism that happens in biological contexts. But you look at the structure of insulin is a really good example. Where'd it go?
You said it was a disulfide that was together, right?
By a single bond. So insulin has this overall shape to it. It's actually two polypeptides linked together with these. And so basically, in order to keep this cysteine next to that cysteine, they form a disulfide bridge. And that kind of keeps everything locked together. This one's interesting down here because it's basically forcing it to stay in this like hairpin structure. So even though it might normally unfold it everywhere, the cysteines make that disulfide bond, just like the OChem reaction we just looked at, to keep it sort of pinned into place. It's pretty small actually for a protein. It's pretty large for an organic molecule though. This is big enough we call it a protein. Basically, when you get past 10 amino acids long, we don't call it a polypeptide or a small polypeptide anymore, then it's a protein.
That's big for you, because these are all short.
These are all, each one of these is this structure linked together. Basically, your carboxylic acid group will react with the amine from the group next to it to make an amide bond. And so they're all in this big long chain, and the different R groups are given its overall shape because you're getting different structures. So this is one of many reasons why you have to take OChem before you can take upper division biochem, because talking about a disulfide bond, like I can tell you about that in a biochem class, but it's going to make a whole lot more sense if you know what a thiol is. So we'll end there for today. The last two slides are, some practice that we'll start with on Thursday. And then this is the mechanism for making the disulfides. We'll go over this in more detail on Thursday too. All right, so I'll see you all at 1, and I'll have your molecules ready for you to start thinking about your lab final.